We're going to take a look at the 2010 homework assignment. So one thing, number one, it says rank the magnitude of the electric potential at points A, B, and C from greatest to least. Number one being greatest, if the 2 points have the same potential given the same ranking. So one thing that we should note is that the closer we are to a point charge, for example, the bigger the electric potential. So if I had a charge that I'll call Q right here, and I have a point in space here versus here, I'll call this VA, and I'll call this VB. VA is bigger than VB, so we're going to use a similar principle here. We measure from the center of the charge distribution out to the point. So what that tells us is that B has the greatest voltage, and VA and VC are equal because A and C are further out. Okay. Now it says here P is at the origin as shown below, and we have the center of curvature of the charge distribution. So it's kind of like a circle, a chunk of a circle. We want to know the electric potential at point P due to the charge Q. Let's go back and calculate that. So we know that V is 1 over 4 pi epsilon naught dq over r. And we don't need to worry about direction. So we did this before, 1 over 4 pi epsilon naught. And basically, we're told that this is a quarter circle. So again, that's going to be Q over 2 pi r over 4, because it's a quarter circle, times dl over the radius here. We're going to integrate that. And dl is just going to be our quarter circle, so I'm actually getting 1 over 4 pi epsilon naught q over r, because this is going to integrate to 2 pi r over 4, and that'll cancel. All right. So, keeping that in mind, we're going to go ahead and actually use that to the little kinetic energy calculator. So for part C, it says, derive an expression for the speed when releasing from the origin. So that actually works like this. QV is the work done, and that equals 1/2 mv squared for part C. So I'm going to say Q times Q over 4 pi epsilon naught R equals 1/2 mv squared. So when we isolate, we're going to get Q times Q over 2 pi epsilon naught times the m here. We'll take the square root of that, and that gives us the speed. Lastly, it says on the dot representing the center below, we want the electric field. Well, the direction of the electric field is going to go this way, to the right. And then to actually calculate the electric field, let's actually go ahead and do that now. Again, since this is a quarter circle, we can actually figure out some heights and some angle stuff here. So we know this angle, since it's a quarter circle, this is going to be 45 degrees. So let's go ahead. The electric field is going to be 1 over 4 pi epsilon naught. And we're going to integrate from negative 45 to 45 degrees. And that's going to be Q over the length being 2 pi r over 4, which is going to be pi r over 2, but we'll worry about that later, times, now dl we just saw in the video, that's dl here, we're going to rewrite that as r d theta, and we only want the cosine component, and we're going to divide the whole thing by r squared. Continuing on here, we're going to get that the electric field is 1 over 4 pi epsilon naught q over L times 1 over r cosine of theta d theta from negative 45 to positive 45 degrees. Continuing on this integration, we're going to get 1 over 4 pi epsilon naught q over, now let me actually simplify this. L is going to be pi times r divided by 2 times the 1 over r. And this is going to integrate to be sine of theta from negative 45 to positive 45 degrees. So let's simplify even further. We're going to get an electric field equal to q over 4 pi squared epsilon naught times 1 over r squared. And the sine of 45 minus the sine of 45 is going to be radical 2 over 2 minus radical 2 over 2, which is just plain old radical 2. So this ends up being the size of our field in part E. All right, so that's it for the first problem.